Students, the next set of videos goes with section 3.3, rotations.
And now it's time for that ever-popular late afternoon game show, Is the Transformation a Rotation? That's right, every week we come to you showing you lots of transformations, and the question is that transformation a rotation or not? Remember, a rotation is just a transformation where there's some fixed point and some angle where we take an object and just rotate it around that fixed point by that fixed angle. Should we take a look at our first contestant? Let's bring him out here. Here's a lovely pair of geometrical objects, and the question is, this is certainly a transformation, and the question is it a rotation? Let's check it out. Is it possible that this can be rotated through a fixed point to actually get this? Well, to help us out, I will actually put a copy of it here, and let's see if we can, right now live, see if it is a rotation. Put my finger down, and here we go. It's on the move. It's on the move. It's looking good. It's looking good. There's a fixed point where my right finger is, and I seem to be matching up perfectly. And I match up exactly. Yes, it is a rotation. Wow, nicely done. If you guessed yes, you were absolutely correct. And you can see here is actually the point that's fixed, and you can see the angle where you actually go from one to the other. Whoop, 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 whoop. All right, let's give him a hand. Great job, great job. All right, now it's time for our last contestants. Here we go. Two lovely objects. And the question is this transformation a rotation? Let's try it right now live. I'm going to put this here. And what I want to do now is I just want it around a fixed point. I want to rotate and get this. Here we go. Rotate. That doesn't work. Okay, hold on. Rotate. In fact, wait a minute. In fact, let's just take this thing and build it. Oh, look, I can't even build the thing. It's kind of like a reflection. You see, it sort of fits in that way. But this way, it doesn't actually fit in. This is not a rotation. Oh, I'm so sorry. Oh, well. We have some lovely parting gifts for these geometric shapes. Don't worry. And I hope that you enjoyed the transformation game of Is It a Rotation? Where the point is, can you find that point upon which everything has been rotated about? Okay, let's take a look at an application where you can actually see the need to actually do a rotation. What I want us to do is I want us to copy the figure and the angle of rotation, and then draw the rotation of the triangle about point P by an angle of measure A counterclockwise. So here's the scenario. We've got this triangle, we've got a point P, and we're given this angle. And what I want us to do is I want us to take this triangle and I want us to rotate it around this point by this angle. So it kind of has to go up a little bit. Well, what I did here was I actually copied the angle. You can see here's the angle perfectly. And all I have to do is place this angle, this vertex of the angle, at the point P. And then the lower edge right to the first vertex. And now that point is now going to be moved to this line. You see, I'm going to now take this point and swing it by A. And to get it exact, it has to be the same distance away from P that it currently is. So I'm just going to, you can actually use a compass if you had one, or just a piece of string. And I measure that point right here, and I swing it out. When I swing it out, I get right to this point right here. And I'll mark that in green. Oh, and red. So what we just did here was, see, this length is the same as this length, but the angle now is A between them. So under this transformation, when I take that point and swing it by A, it goes there. Okay, what about this point right here? Well, I did the exact same thing. I put the vertex of the angle right at P and put this lower part of the angle to here. And I just have to now measure that distance from P to that vertex, and then find that exact same distance here, which I'll mark in red. And so what I see here is that this vertex, when swung by a rotation of A, goes to there. See? And finally, what about this point? Well, I did the exact same thing. I put the vertex of the angle P and the right edge at that vertex. Measure that length exactly. Swing it over. It's right here. And so if this point gets swung, rotated by measure of angle A, it goes to here. And so what about the whole triangle? Doing it right now live. Live rotations. Thought about live rotations? You want to see live rotations? You might have even dreamed about live rotations, and here it is. Your dreams come true. And that's it. What we just did was we took this triangle and we rotated it by that angle. And if I do it sort of live, it goes there. And that's how it looks. So that's actually how you can actually geometrically produce such rotations. If you have an angle, just copy the angle and actually swing it out, and you can actually produce. This thing gets rotated today. I'll see you soon. All right, let's take a look at a rotation that actually happens in the coordinate plane. So in this case, what I see here is a triangle in the coordinate plane, A, B, C, and you can see the coordinates of those points. And what I want us to do is I want us to rotate triangle ABC by 90 degrees in a counterclockwise direction about the origin. So what that means is I want to actually take this triangle, and around this point, I want to change things by 90 degrees. I can actually do it for you visually, just for fun, if you understand that this is not going to be quite right because the axes are going to be wrong. But you just want to see what it's going to look like visually, check it out. That's the answer. This has got to be the y, and that's got to be the x. But visually, when we fix things up, if you sort of hide those things a little bit, visually it's going to be in the third quadrant. That's what we see here. And the reason is because I just did exactly what I advertised. I just rotated about the origin by 90 degrees, counterclockwise. Let's confirm that. And we'll confirm that by thinking about exactly what the actual rotation would look like. Well, let's see. If I take an arbitrary point that has coordinates x, comma, y, where would it get sent to under this transformation? Well, under this transformation, what happens to x? Well, x would actually become, if you think about it for a second, the x value for the new thing would become the negative y of the old thing. And the new y would be the old x. Let's do this in action just for fun. Let's pick this point here. That's 4, 0. If I rotate that point about the origin by 90 degrees, where's it going to go? It's going to go up here, which you see now is 0, 4. So 4, 0 goes to 0. That's negative 0, 4. Checks. But what if I took the point, let's say, 0, 3, and rotated 90 degrees counterclockwise? Then it goes all the way to negative 3, 0. So 0, 3 goes to negative 3, 0. You can see this transformation actually works. So let's see where everyone goes. So where is A going to get mapped to? Well, what I send it to is negative y, which is going to be negative 1, comma, negative 1. So negative 1, comma, negative 1 is right here. That's going to be the A prime. A prime is how we mark the image of A under this map, which is going to be the point that has coordinates negative 1, comma, negative 1. All right, what about B? Where does B go to? Well, under this map, we see it goes to negative 2, comma, negative 4. So negative 2, comma, negative 4, that's exactly the coordinates for B prime. And what about C? Well, under this map, negative 2, comma, 5 goes to negative 5, comma, negative 2. Negative 5, comma, negative 2 is right here, That's C prime. And if you remember our sort of informal, just fun, silly attempt where I just actually turned the entire picture, rotated the whole picture by 90 degrees counterclockwise, we saw the triangle all of a sudden appear what seemed like to be the third quadrant. We now see is the reality, because there is in fact the rotation. You can see it for yourself. You took this thing and rotated it out 90 degrees, you get this picture right here. Perfect. You know, water grist mills are great. They're beautiful to look at, and they're so dynamic because the water actually goes around the mill. So actually, let's take a look at a particular one that I'm thinking about. It has a radius of 6 feet, and it takes 5 seconds to make a complete rotation. A bucket of water starts at position 60. The question is, what are the coordinates of the bucket's location after 2 seconds? A lot of stuff to think through here. We really have to sort of focus on what's going on. So first of all, here's the image. And you can see the origins at the very center of the mill. And you can see here is 6, 0. And we know that we go around once in 5 seconds. And the question is, if we start here, how far do we go around after 2 seconds? Well, let's think about that. First of all, we can do a little bit of guessing. 5 seconds gets us all the way around, which means how far would it take us to get halfway around? That would be half of 5, which is 2.5 seconds. So 2.5 seconds gets us to here. This is less than that. It's only 2 seconds, so we're probably going to be somewhere up here. That gives us a sense of what we should be thinking about. Now let's see how accurate our sense is and make it precise. So, first of all, 2 seconds. Well, how much around have we gone? Well, if once around takes 5 seconds, then the amount we've gone in 2 seconds is 2/5 of a complete rotation. Well, okay, now if it's 360 degrees in a full rotation, then we multiply this by 360 degrees to find out how many degrees I've traveled starting from this point. And if we actually perform the division and multiplication, we see 144 degrees. Aha! Which notice is less than 180, which is the full thing around. So 144 degrees, I'm just going to eyeball this. This might not be exact, so don't get mad at me. But just roughly speaking, let's say 144. 144, let's say, is right here. Okay? So I'm going to declare this to be 144 degrees. Okay, if that's 144 degrees, I can actually find this because this angle and this angle are supplementary. I take 180 and subtract 144, and I see 36. So right in there, that little teeny sliver of an angle, invisible maybe to most people, but not to us, that's 36 degrees. We want the coordinates of this point, which we now see can be viewed as the vertex of a particular right triangle. Great. Well, now I can actually use trigonometry to figure out this length and this length. I know this length because remember, this point here is the point that's circulating around, and I know that it has length 6, 0. So this radius, if you will, is 6. So somehow a cosine must come into play here and a sine must come into play here. Let's check it out together. So to find this length right here, which we see is plainly negative, what I see here is that the cosine of 36 degrees is going to equal adjacent, which is x, over hypotenuse, which is 6. But we know the answer has to be negative, so really it's negative x. Well, now solving for x is easy. I multiply everything through by 6, and then everything through by a -1. And I see x equals -6 cosine 36 degrees, which we can use a calculator to actually estimate exactly. Well, you can't estimate exactly, but you can estimate. And so I see x is approximately -4.9 feet. All right, so this length right here is 4.9 feet, but it's in the negative direction. So that point, -4.9. What about the height? Well, for the height, we have an opposite side, so we're going to obviously use sine, and remember that sine of 36 degrees is going to equal opposite y divided by the hypotenuse, which is 6. So multiplying through both sides by 6, I see y equals 6 sine 36. Notice it's positive, it's going up, so that's good. We don't have to worry about that negative sign like we did here. And we plug this in my calculator to get a rough sense of what this is. We see about 3.5 feet. So this is 3.5. So what are the coordinates at that point? The coordinates at that point we were searching for, x value is approximately negative 4.9. Y value is 3.5. So you can see how important the trigonometry is. It really comes into play. It allows us to actually do something. But then also you can see how this point is really being rotated. We were able to actually find the rotation after 2 seconds. Turns out it was 144 degrees. And then using some sines and cosines, and then using a calculator, get a rough sense of where that point is. Pretty cool. Anyway, congratulations thinking about rotations. I will see you soon.